Are your neural networks not performing as well as you are like? Stick about because today we will cover the most important optimization techniques to improve your model performance. Welcome back to codeRebel. I am Shivam and today videos we are diving deep into some of the most powerful optimization techniques used in a neural network. If you are struggling with training your models or looking for ways to speed up convergence while increasing accuracy, then this is video for you. We'll go through optimization algorithms like gradient descent, SGD, Adam and more. I will show you the code and explain how to optimize work in practice using simple explanations and graph. Let's start the optimization techniques in neural network. In machine learning and deep learning, optimization refers to minimizing the loss of function, which tell us how far the predicted output are for true values. The lower the loss, the better the model. An optimizer is an algorithm that's help adjust the weight and learning rate of the model is to reduce this loss. These optimization techniques are essentials to ensure your neural network is learning correctly and efficiently. Optimization refers to the process of minimizing the loss function in neural network. This is our first key point. Optimization adjusts the weight and learning rate to reduce the error and improve the performance. In this presentation, we will explore the 9 optimization algorithms and their applications. In this video, we will explore the 9 optimization algorithms, which code will be clear code example for each. We will explain how they work, where they used, and the process and constants of each optimizations. Let's start the first algorithm is gradient descent. Gradient descent is one of the most basic and widely used optimization algorithm. Its work for computing the gradient or slope of the loss function with the respect of the weights and moving the weights in the direction that reduces the loss. This is a main key point here. The iterative algorithm minimizing the loss functions here adjusts the weight and opposite the direction of the gradient. This is a code implementation. Learning rate is equals to 0.1 for I in range equals to n. Iteration gradient, compute gradient data, weight, learning rate and gradient. Let's see our VS Code up. Let's see our Google Colab and update. First one, import the numpys. With each iteration, the weights are updated in a small step to minimize the loss. The learning rate control how to large these steps. First one is generate some sample data here. After that, add some bias terms here. Gradient descent function use here, x and y, learning rate 0.1 and an iteration number of iteration we use here. Here is a run gradient descent, display the estimation parameter, we used theta here. pld.scatterplot we used here, plotting of the dot function theta. We have different small steps to minimize the losses. The learning rate control how to large these steps are. This is the gradient descent optimization code here. one of the data point at a time. Only they used for only a data times at a time. This means makes the process faster by introducing some noises and these training data. A single data point used, and this is a code example demo code here. For I range for the n number of iteration here, random sample, we use here random sample np.random.choice data. Here is a gradient, compute gradient, random sample, and here we slice for the weight. Let's move ahead for a coding apart also. Here is a code for a SGD. Update the model parameter using these data only at a point. Instead of using the entire data set like gradient descent, SGD uses only the data at this time. SGD perform faster, but because it's only look at the one data points at a time, it can bounce around the minimum. Here is a code. Here is a graph of the SGD. Here is a graph for the mini batch SGD. Mini batch SGD strikes a balance between the gradient descent and SGD by updating weights using a small random batches of data instead of a single sample or the entire data set. Here is a code. Here is a mini batch SGD. Define the data, learning rate and batch size. Here the code for I length, data batch or size. Here execute the mini batch SGD and plotting the mini batch SGD. Using mini batch SGD can improve both the speed and the stability of the learning process. Fourth one is SGD with momentum. Momentum address a memory component to SGD, allowing the model to move faster in the right direction and avoid the local minima. SGD with momentum function here. Initialize, define the learning rate of the number of iteration here. Learning rate is 0.1. Execute the SGD with momentum, result momentum, history momentum, SGD with momentum, learning rate momentum 0.9, number of iteration here. And after that, plotting the SGD with momentum. Think of a momentum as a pushing a ball down a hill. Once it's gain speed, it's continue the rolling even into this slope and flatten. This is like a flatten SGD with momentum. And naturally accelerated gradient energy, known as energy, improve upon momentum by looking ahead before making an update, which leads to faster to convergence. Here is a for I and a in range number of iteration. Look at x plus momentum dot velocity gradient to star. Look at velocity is equals to momentum star velocity minus learning rate stars gradient weight plus equals to velocity. Here is execute the natural accelerated gradient result, nag history and the learning rate, momentum and iterations, and after plotting. By looking ahead, energy helps correct courses faster than standard momentum. Sixth one is adaptive gradient, known as grades. Adapt the learning rate for each parameter individually, which works well for sparse data but can causes the learning rate to shrink too fast. Here's a grade is equals to grade squared sum is equals to 0 for I n range number of iteration gradient, At boost, execute the Adam grades, and here the plotting the Ada grids. Ada grid is used for dealing with data that has sparse gradient like text and images data. Ada delta is a variant for the Ada grids that restrict the window of accumulated past gradient to a fixed size, preventing the learning rate from shrinking too much. Here is a code for Ada delta. After the execution of the code, here is the graph, value of x and iteration. Ada delta ensure the learning continues without decaying too fast. RMSprop is a root means square propagation, helps handle the problem of Ada grids by keeping a view running averages of the squared gradient. Here is executions of the code here for I and number of iteration gradient 2 into star x a gradient for the decay and gradient, adjust LR learning rate and NP numpy the square root. RMSprop works well for online learning tasks and helps avoid issues with Ada grades. Number 9 is adaptive momentum estimation. Adam combines the benefit of the Ada grades and RMSprop, adjusting the learning rate for each parameter based on the both first momentum mean and second momentum is variance of the gradient. Here is a graph for the Adam is a very popular optimization because it adapts the learning rate and performs well across many tasks. Here is a conclusion. We have worked a lot of ground today. As you can see, different optimization techniques have different strengths, and it is important to choose that one best suit your model and data set. Adam is a great starting point for most problems, but don't be afraid to experiment with other like Ada grids and SGD with momentum. Here is a conclusion of these code here. Import numpy, macro gradient descent, SGD, mini batch stochastic gradient descent, SGD with momentum, NAG, adaptive gradient, Ada delta, RMS, adaptive momentum. Here is a setup for the comparisons here. Run optimization result.grid. Here is these 9 steps of the optimization. Here is a plotting of these results here. After that comparison of optimization, these techniques, which techniques is better than of the comparison of these techniques. Gradient descents and Ada boost, Ada grid and SGD with momentum. Here is a result. With these optimization techniques, your neural network will converge faster and be more accurate. Try these out in your own project to reach significant improvement. Here is some basic regularization techniques improve neural network. First one, import necessary libraries here. Generate the static training data. Replace your actual data, but whatever you actual data with use here. X-train and Y-train data here. Define your models. Model means sequentials. Define the learning rate schedule. After that, compile the models. Initialize the learning rate scheduler. Fit the model and store training history. And after that, 7 step is plotting the training loss and approaches. Here is a model loss and approaches. Here is a learning rate and learning rate schedules. Same things here, learning rate schedules, approaches and learning rate. And thanks for watching. If you found this video helpful, please give it a like and subscribe to codeRebel for more content on AI, machine learning and coding. See you in the next video.